So as we do every week, we're going to recap what we did last week and now forecast what we're going to do this week. So last week we had a major lecture series on linear classifiers. We started with the very basic perceptron learning algorithm, which is just going to take a separating hyperplane and adjust it to cater for misclassifications until they're corrected. We saw in a noise-free environment, this perceptron learning algorithm is guaranteed to converge. We also went from general linear classifiers to the idea of linear regression, as well as logistic regression. In linear regression, we get real-valued outputs, and we are going to penalize misclassifications by their squared error. The idea that small mistakes don't matter a lot, but large ones are upsized proportionally in counting for how they should be adjusting the hyperplane. In logistic regression, we're going to do the same, but logistic regression is actually outputting a probability value that we can interpret for binary classification. Both of these different types of regression output scores that are going to be similar to linear classification in being a point-wise loss. We're going to take the point-wise loss in all three of these cases and then take their average in order to define a whole cost function that we're going to optimize. Now, how do we optimize that cost function? We saw that as long as we have a smooth gradient or derivative, then we have no problems. We can find the stopping point where the acceleration or the slope tends to zero and then find the correct answer there. We can either do it directly through the normal equation for linear regression or in a gradient descent manner, which only depends on the first derivative. In gradient descent, we take steps in the opposite direction of the gradient towards minimizing the cost. And we saw that when we take a stochastic version of this, which basically shows that over lots of steps, the average gradient of individual points converges to the batch, we can get the same results. This is a great savings because now we can use a constant step instead of a step that's costing proportional to linear of the size of the data. Now let's take a look at what we're going to learn this week. This week we're going to look at a very key part of bias and variance. It is basically an extension of what we learned in week 2 on concept learning. We're going to see why when we have a very powerful model, we have a lot of capability to fit all of the nuances of the training data. In fact, probably too much, in the sense that some things that are in the training data are particularities of the data set that we sampled, and not something general that we should be capturing that's for the entire distribution, including the test data. When this overfitting occurs, we will see that it has a component that's actually due to the model complexity, another one that's due to the sample data set. This is the bias-variance trade-off. We're going to see that we can apply this bias and variance analysis to decompose the case of analysis for models that are simple, both with and without noise. And finally, just in the pre-lecture, so that you get some idea and intuition, we're going to finish the linear models unit. We're going to look at a particular learner called the support vector machine, or SVM. This is a really neat model that I like a lot myself. It's the idea of extending the perceptron learning algorithm to try to place the hyperplane in an optimal position. We're going to see how that generalizes from the idea that we should be trying to put as much distance between the two types of points, positive and negative spaces, which we're going to call the margin. We're going to understand why the SVM is actually really interesting because it has a model complexity based on these specific points, which we call the support vectors. And we're going to extend this idea of the support vector machine to cater for noisy examples, something that the perceptron learning algorithm couldn't do. We're going to introduce the idea of slack variables that allows some measure of tolerance for mistakes in the hyperplane classification and build that into the loss function, which we can then optimize.